Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorial titled Introduction to Laplace Transforms, we studied the basics of Laplace transforms. We learned the meaning, the definition, and also we obtained the Laplace transform of simple functions. We also understood to transform the given network using Laplace transforms. During this tutorial, we shall discuss regarding the signal waveforms such as sinusoidal, non-sinusoidal, periodic and non-periodic waveforms. We also discuss about the step function and the delayed step function. Hope the discussion will be lively and interesting. Friends, you know that a signal in a network is a time varying function. It may have different shapes and characteristics. The shapes of the waveform could be sinusoidal or non-sinusoidal. The characteristic could be periodic or non-periodic or pulse type. First, let us understand the meaning and the difference between different signals. Consider a sinusoidal signal shown in figure. You know that it follows a sine law. It has a maximum amplitude of Vm or Im as the case may be. The signal shown has an angular frequency of omega radian per second, and you know omega is equal to 2 pi f, where f is in hertz. The signal is a periodic as it follows the property f of t is equal to f of t plus capital T, where capital T is its period, and you know f is equal to 1 upon capital T. It is a continuous signal, but non-sinusoidal signals do not follow either a sine law or a cosine law. Please note it. Few examples of non-sinusoidal signals are shown in figure. The first one is a step function, second is a pulse function, third is a ramp function, and the fourth is an impulse function. Note that all signals are represented for t greater than or equal to 0. Friends, these are only some examples of non-sinusoidal functions. We shall study their characteristics, mathematical model, and their Laplace transform and so on in different tutorial sessions. But now, in this tutorial, we shall study a step input function in detail. Friends, a step function is one which changes in magnitude abruptly from one value to another at time t is equal to 0 or at any time of t after t is equal to 0. As already expressed, a step function is a discontinuous signal. Consider a step function shown in figure. You see that the magnitude of the function changes suddenly from 0 to a units at time t is equal to 0. For time t less than 0, the magnitude is 0. For t greater than or equal to 0 plus, the magnitude is a units. At this stage, let me clarify regarding three time events. One t is equal to 0, another t is equal to 0 minus, and the third t is equal to 0 plus. Consider the time axis shown in figure. You will see three time events. One at t is equal to 0, second at t is equal to 0 minus, and the third at t is equal to 0 plus. Let me now define these time events. Event at time t is equal to 0 minus can be defined as an event very close to t is equal to 0 on negative time axis. Similarly, an event at time t is equal to 0 plus can be defined as an event very close to t is equal to 0 on the positive time axis. Fine, friends. But these points could still be closer to time t is equal to 0, isn't it? So, now consider another 2 points which are still closer than the earlier points as shown in figure. But friends, however closer these points are, still all three events are considered as different time events. This point you have to remember. Now, consider a step function of a units as shown in figure. It can be represented mathematically as f of t is equal to 0 for t less than 0 and it is equal to a for t greater than or equal to 0. Note that the function changes its magnitude suddenly from 0 to a units at t is equal to 0. So, this step function is said to occur at t is equal to 0. Friends, now let us study unit step function. It is very simple, friends. If the magnitude or the strength of the function a is equal to 1 unit, then the function is called as unit step function and it is denoted as u of t as shown in figure. Now, you know its mathematical model f of t is equal to 0 for t less than 0 and is equal to 1 for t greater than or equal to 0. That is simple. Friends, a unit step function u of t is an important function in circuit analysis of special signal waveforms because many other wave functions can be expressed in terms of u of t. This aspect we shall see as we go further. Now, let us find the Laplace transform of a unit step function. We know that unit step function mathematically is expressed as f of t is equal to 0 for t less than 0 and is equal to 1 for t greater than or equal to 0. So, by definition, we know that L of f of t is equal to integration 0 to infinity f of t into e to the power of minus st dt. By substituting the value of f of t, we get L of f of t is equal to integration from 0 to infinity 1 into e to the power of minus st dt. By integrating, we get L of f of t is equal to minus into bracket e to the power of minus st by s limits ranging from 0 to infinity. By substituting the limits, we get L of f of t is equal to L of u of t is equal to 1 upon s. Friends, now if I ask you, how can I represent a step function shown in figure 1? It is simple. F of t is equal to a into u of t. Its Laplace transform L of f of t is equal to a divided by s. Also say, if V is equal to 10 volts, its Laplace transform capital V of s is equal to 10 divided by s. Hope it is clear to you. Friends, next we shall learn about time shifted or delayed step function. We know that the wave functions may occur at any time after t is equal to 0. Remember, we express all functions for time t greater than or equal to 0. Now, observe the given step function shown in figure. It is a voltage step function. It has a strength of 1 volt, so it can be called as a unit step function. Its magnitude is abruptly changing at t is equal to 1 second, hence it can be called as a delayed step function. Also, it can be called as a delayed unit step which occurs at t is equal to 1 second. Its mathematical model is v of t is equal to 0 for t less than 1 second and is equal to 1 for t greater than or equal to 1 second. That is simple. Similarly, consider another delayed step function shown in figure. Observe the given step function. It is a current delayed step function. It has a strength of 4 amperes and it occurs at t is equal to 2 seconds. Note that. So, it can be represented as I of t is equal to 4u of t minus 2. Friends, now let us find the Laplace transform of a time shifted or delayed unit step function. Consider a delayed unit step function delayed by a seconds as shown in figure. This function can be represented as f of t is equal to u of t minus a, and mathematically f of t is equal to 0 for t less than a seconds and is equal to 1 for t greater than or equal to a seconds. So, L of f of t minus a by definition is equal to integration from 0 to infinity f of t minus a into e to the power of minus st dt. Since f of t occurs at t is equal to a, we can write L of f of t minus a is equal to integration from a to infinity f of t minus a into e to the power of minus st dt. By substituting the values, we get L of f of t minus a is equal to integration a to infinity 1 into e to the power of minus st dt. By integrating, we get L of f of t minus a is equal to minus into bracket e to the power of minus st divided by s limits from a to infinity. By substituting the limits, we get L of f of t minus a is equal to e to the power of minus as into 1 divided by s. So, we see that if a unit step function is delayed by say a seconds, its Laplace transform will be e to the power of minus as into L of u of t. Hope you got it. Friends, now let us see what is a negative step function. We know that we represent functions for t greater than or equal to 0, but there could be a negative step function whose magnitude abruptly changes on the negative magnitude axis. So, here are two negative step functions represented in figure. Observe figure 1. Its magnitude changes at t is equal to 0 on the negative side axis. It has a strength of minus 1 unit. So, it can be called as a negative unit step function which occurs at t is equal to 0. It can be represented as f of t is equal to minus u of t, and L of minus u of t is equal to minus 1 over s. That is simple. Now, observe figure 2. It is also a negative step function. It has a strength of minus 5 units. It occurs at t is equal to 3 seconds. So, f of t is equal to minus 5 u of t minus 3, and L of f of t is equal to minus 5 into e to the power of minus 3s divided by s. Friends, I hope you can represent any step function given and find its Laplace transform now. Friends, the time delay property of any function can be viewed in general, and we call this property as time shifting theorem. Sometimes it also is called as time displacement theorem. Now, let us provide proof for the time displacement theorem. Friends, properties of Laplace transforms become handy when Laplace transform of a given waveform is to be obtained. Consider a delayed function f of t. Let the delay be a seconds. Then the delayed function is represented as f of t is equal to f of t minus a. You know that. And L of f of t minus a by definition is equal to integration from 0 to infinity f of t minus a into e to the power of minus st dt. Now, to prove the displacement theorem, let us change the time variable from t to tau plus a, where a is constant, that is a seconds. You know that. If t is equal to tau plus a, then number 1, t minus a is equal to tau. And if t is equal to tau plus a, if we differentiate it, dt is equal to d tau plus 0, because a is constant. So, the equation for L of f of t minus a can be written as L of f of t minus a is equal to integration from 0 to infinity f of tau into e to the power of minus s into bracket tau plus a into d tau. In the term e to the power of minus s into bracket tau plus a, e to the power of minus as is constant. Note that. So we can take it out, and thus we get L of f of t minus a is equal to e to the power of minus as into integration from 0 to infinity f of tau into e to the power of minus s tau d tau. This is nothing but f of s. So L of f of t minus a is equal to e to the power of minus as into f of s. This shows that the Laplace transform of any delayed function f of t delayed by time a seconds is e to the power of minus as times the Laplace transform of a function. Friends, to emphasize the concept we have learnt, let us solve two examples. In the first example, four functions of time are given. f1 of t is equal to 2u of t minus 1, f2 of t is equal to 5u of t minus 3, and f3 of t is equal to minus 5u of t minus 5, and finally f4 of t is equal to minus 2u of t minus 7. We are required to find the sum of all the functions f of t and represent f of t in the form of a plot and find its Laplace transform. First, let us understand each function given. The first function f1 of t is equal to 2u of t minus 1. This is a positive step of 2 units which occurs at t is equal to 1 seconds as shown. To plot f of t, let us add this function as shown. The second function is f2 of t is equal to 5u of t minus 3, and you know it also is a positive step function of 5 units which occurs at t is equal to 3 seconds as shown. If we add f2, we get the waveform as shown. Note the magnitude increases by 2 plus 5, 7 units at t is equal to 3 seconds. Next, f3 of t is equal to minus 5u of t minus 5. This is a negative step of 5 units which occurs at t is equal to 5 seconds as shown in figure. If we add f3, the magnitude reduces by 5 units at t is equal to 5 seconds. Note it. Finally, f4 of t is equal to minus 2u of t minus 7. This also is a negative step function which occurs at t is equal to 7 seconds as shown. If we add f4 now, we see that the magnitude of the resultant function f of t reduces to 0 as shown. So, we get the final plot as shown in figure. The remaining solution is simple, friends. We have f of t is equal to f1 of t plus f2 of t plus f3 of t plus f4 of t. By substituting the values, we get f of t is equal to 2u of t minus 1 plus 5u of t minus 3 minus 5u of t minus 5 minus 2u of t minus 7. By taking the Laplace transforms, we get f of s is equal to 2 e to the power of minus s by s plus 5 e to the power of minus 3s by s minus 5 e to the power of minus 5s by s minus 2 e to the power of minus 7s by s. Friends, finally, let us solve another example to find f of t given f of s is equal to 5 divided by s into bracket e to the power of minus s minus e to the power of minus 3s. Consider the equation. This equation can be written as f of s is equal to 5u into e to the power of minus s divided by s minus 5 e to the power of minus 3s by s. The first term shows that it is a Laplace transform of a delayed positive step function of 5 units delayed by 1 second. Hence, say f1 of t is equal to 5 u of t minus 1 as shown in figure. Similarly, the second term is delayed negative step of 5 units which occurs at t is equal to 3 seconds. Hence, say f2 of t is equal to minus 5 u of t minus 3 as shown in figure. So, by adding f1 of t and f2 of t, we get f of t is equal to 5u of t minus 1 minus 5u of t minus 3. That is simple. The resultant waveform is plotted as shown in figure. Friends, finally, let me summarize. In this tutorial, we understood the difference between sinusoidal, non-sinusoidal functions. We defined and obtained the mathematical model of the positive and negative step functions. We also discussed regarding unit step and delayed unit step. We defined a time displacement theorem and proved it. We also solved problems to emphasize the concepts learned. During the next tutorial, we shall study the remaining special functions. Hope you understood the concept of step functions. If this tutorial has kindled some of your thoughts, please forward your feedback and suggestions to my email. Thank you for watching this video.